Hello everyone. This week we are going to learn about the inductance, capacitance, and the mutual inductance. Let us start with the class. So the presentation outline is we will learn about the inductors. Then we will learn about the capacitors, the current voltage relationship, the energy and the power relationships. Then we will learn about the series parallel combinations of inductance and capacitance. Then we will, proceed with the mutual inductance, and we will take a closer look at the mutual inductance. As all you know, we are surrounded by lots of interesting gadgets and stuff. One thing that we use in practical life is proximity switches. Sometimes designers prefer to use switches without moving parts because of reliability issues, because this increase the safety, reliability, convenience, and novelty of their products. So this kind of switches are called the proximity switches. And this can employ a variety of sensor technologies. For example, some of the elevator doors stay open whenever a light beam is obstructed. We will now introduce the design of some, capacitive touch sensitive switch at the end of this chapter to give you some practical insight about how we use capacitors and inductors in practical life applications. Now, how do we define an inductor? Basically, inductor is the simplest circuit element because you just need a wire and you just need to create a coil with that wire and you have the inductor. Basically, the symbol is shown like this. It resembles a resistor, but it has, half circles, like it represents the coil structure, physical structure of the inductor. So the inductance is represented by L, symbol L, and the units for L is henries, and it's basically a consequence of conductor linking a magnetic field. Okay, inductors typically store energy in magnetic field, and the voltage and the current relationship is shown like this. Here the direction of current is always taken with respect to the positive voltage point. So the voltage difference is as shown here, and the current will flow from the positive voltage to negative voltage. The direction is always like this. So the reference direction is assigned with respect to the voltage drop across the terminals of the inductor. Okay, and the relationship between the voltage and the current is what makes inductor interesting. Basically, the voltage across the inductor is proportional to the inductance of the inductor and proportional also to the time derivative of the current across the inductor. Basically, voltage equals to L times di over dt. This is interesting because the voltage is proportional not directly to the current, but it's proportional to its derivative. This has interesting, features that introduce us, especially in practice. But sometimes it's an advantage and sometimes it's a disadvantage that we would like to avoid. Let us learn more about this relationship. So the current, if the current is constant, like if we connect a battery, for instance, a DC voltage source across the inductor, then the voltage across the ideal inductor becomes zero. Basically, it's just a short circuit because the inductor behaves like a short circuit for DC current. How can we observe it? If you go back, if the current is constant, then its time derivative will be zero. Then this means that the voltage across the inductor will be zero. If the voltage across any component is zero, it means there is a short circuit between the terminals. So this is why we observe that inductor behaves like a short circuit in the presence of a constant DC current. So inductance is more useful with time varying currents, which means the alternating currents. It will show some impedance. It will impede the flow of current when the current is depending on time. Another observation that we can make at this point is the current cannot change instantaneously in an inductor, which means that the current cannot change by a finite amount in zero time. Now, if we again look in our basic terminal equation for the inductor, we observe that the change of the current has to be within an interval. If the current changes instantaneously, that is, if this dt is very small, then I'm going to get a very large voltage across it. And this might be dangerous for other components that are connected to this inductor. We can also exploit this feature. That is, if we are able to switch the current on and off across the inductor, then we can generate higher voltages than the regular circuit voltages. This is how we use switch mode. This is what we use basically in step-up type switch mode power supplies. We make use of this feature. We switch this current on and off in a controlled manner so that we can control the voltage across the inductor, and we use that voltage to provide power to our circuit. So the second observation is that the change of current cannot happen in zero time. So this is kind of a mechanical. You can think of it like an inertia in the mechanical domain in physics. So in order for current to change, it needs some time. And if this time is very small, then the voltage has to be very high to counterbalance the expression. So if you try to change the current across the inductor in a very short amount of time, then you will have a very large voltage drop across the inductor. And in certain circuits, in practical circuits, this can cause arcing, which can be dangerous. Sometimes, for instance, when you plug your laptop adapter or phone charger into the wall plug, you can hear the buzzing sound of arcs because there might be some inductors that just causing the inrush current, and if it's not properly designed to damp that current, you can simply observe this arcing. For instance, in cars, we use this feature to ignite the fuel in the pistons so that like the engine can operate. Or in high voltage operating bug zappers that we use to avoid bugs at home, we use inductors again to increase the voltage and create some arc when a bug enters between the terminals of the component. So in practical life, there are many interesting applications of this, but in regular circuit design, we have to make sure that the voltage across this inductor is controlled, because if you indefinitely let the voltage increase, then other components connected, especially the semiconductors, they are very sensitive to high voltages, they can get damaged. Okay, so Like sometimes you can make also can encounter this event when you are turning on and off some circuit that contains an inductor. When this on and off event occurs, actually it can be represented mathematically by a step function or a delta Dirac function, which occupies very short amount of time. So a very high voltage can be generated across the connected inductor, which will cause arcing. Basically, you create a little lightning, which also creates some sound. Sometimes, if you are in the dark, you can see it. The current initially continues to flow in the air across the terminals, which is called, arcing. Uh, but this must be, controlled. Otherwise, you can get your equipment or you can get your circuit components damaged. Okay. Let us take a closer look to inductor through an example, so that we can understand how the current and the voltage behaves over the component. Let us assume that we have an independent current source connected to an 100 millihenry inductor, and the independent current source in the circuit generates zero current when the time is smaller than zero. And when the circuit is turned on at t equals 0, it creates a pulse of form 10t times e to the minus 5t amps for t greater than 0. So uh, this function is partially defined. The current is partially defined. So when the t is smaller than 0, we have I equals 0. And when the t is greater than 0, we have I equals to 10t times e to the minus 5t amps. So we are asked to sketch the current waveform. At what instance of time is the current is maximum? uh, Express the voltage across the terminals of the inductor as a function of time, which we can do because we know the relationship between the voltage and the current in an inductor. We have just learned, so we can use that relationship to compute the required things. And we can sketch the voltage waveform once we know the mathematical expression. Are the voltage and the current at a maximum at the same time? This is interesting question. For instance, in resistors, V equals to I times R. So whenever the voltage changes, the current follows. So when the voltage is maximized, the current is also maximized. However, in inductors and in capacitors, the voltage and the current relationship is pretty different. So we will see that we cannot reach the voltage maximum or the current maximum at the same time. There will be some difference in time, which is called the phase difference for these maximum points. At what instant of time does the voltage change polarity? Is there ever an instantaneous change in voltage across the inductor? If so, at what time? Now, let's take a closer look and try to answer these questions, because each answer to these questions will help us to understand the behavior of the inductor in a better way. So, the current, if we draw the function for t smaller than 0, we have 0 current, as you can see here. And for t greater than 0, we have the function defined as given. Okay. As you can see, this is a current that changes with respect to time. So it's not a constant current. So in this case, I will have some voltage because the voltage will not be 0. And I just need to compute the voltage across the inductor by taking the derivative of this current and multiply it with the inductance value. Inductance value is constant. We have 100 millihenry inductance. So we have to compute the derivative of this function. So di over dt can be computed because if we do the math, it's going to be 10 times minus 5t e to the minus 5t plus e to the minus 5t. And if you do the math, it's going to be 10 times e to the minus 5t in parentheses 1 minus 5t amps over seconds. Okay. Now, when this thing becomes zero, we can actually see that the exponential decaying function will never be zero. So this term 1 minus 5t can be zero, especially when t equals to 1 over 5. So when t equals to 200 milliseconds, as you can see here, the derivative becomes zero. And we know that when the derivative is zero, we are at some extreme point. So if you get either the maximum or the minimum value. So this is an important point for us to inspect. And we have found it, basically. This concludes part B. In part C, we need to compute the voltage. So I know the di over dt. And the voltage across the inductor is defined as L times di over dt. So I just need to multiply it with this constant, L. That would give me 0.1 times 10 times e to the minus 5t times 1 minus 5t. Okay. If we do the math, it's e to the minus 5t times 1 minus 5t volts for t greater than 0. And it's 0 for t smaller than 0 because, as you can see, we have 0 current here. And if you take the derivative, it will be also 0. So the voltage will be 0 when the t is smaller than 0. So we can now take a look at the d in which we are supposed to draw this function. This is the voltage across the inductor. And the voltage becomes 0 at 0.2 seconds, as we have mentioned. This is an important point since the derivative of the current becomes 0. Now, for the question E, the voltage and the current are not maximum at the same time. As you can see, like here we have the current waveform, and here we have the voltage waveform. If we align them in time and take a look, here the voltage maximum is at t equals to 0, and the current maximum is t equals to 0.2. So there is some time difference between two maximum points for the current and the voltage. As a result, like the reason is the voltage is proportional to the derivative of the current. It's not directly proportional to the current, as in the case of a resistor. So there is time difference between the maximum points because of that. For the part F, in which we were asked at what instance of time does the voltage change polarity? Well, at 0.2 seconds, which corresponds to the moment when the derivative of the current is passing through 0 and it's changing the sign. So as you can see here, the voltage is positive between 0 and 0.2, and it's negative between 0.2 and 0.6, as you can see here, okay? So the polarity changes at 0.2. And for the part G, is there ever an instantaneous change in voltage across the inductor? If so, at what time? As you can see, we have polarity change at 0.2. So there is also the polarity change at t smaller than 0 and t larger than 0. So the voltage can change instantaneously. However, the current has to change in a slower or in a steeper, fashion. It cannot instantaneously change. However, the voltage can change instantaneously. As you can see, there is a jump here at t equals to 0. the voltage jumps, but the current is typically always continuous, has to be continuous. If there are jumps in the current, then it means you are going to get very high voltages between the terminals, because when you solve the terminal equations, it will give you large values. So the current in an inductor, in terms of the voltage across the inductor, can be written as V equals to L times di over dt. Now from here I can pull my dt next to the voltage. Then I can rewrite it as V times dt equals L times di. If I integrate both sides with respect to the variables, so with respect to the variables, I'm going to get L times IT from IT0, which is the initial current, to some IT, and I use a dummy integration variable here as X. It's not important because these boundaries will replace that X. I can equate this to the integral of voltage d tau. Again, tau is the integration variable, which is dummy. The boundaries are from t0 to t. T0 is the initial time, and IT0 is the corresponding current at t equals to t0. If we simply do the math, we can simply define the current across the terminals of an inductor as 1 over L times integral from t0 to t v times dt plus I t0. Okay, IT0 is the initial current if it exists for the inductor, plus some term that's inversely proportional to the inductance and proportional to the voltage, as you can see, the integral of the time integral of the voltage. So if we assume that t0 equals to 0, then we are going to get the IT relationship that we derive from the voltage to current relationship, original relationship, as 1 over L from 0 to t v dt plus I0. So we need to remember this voltage relationship, and the current relationship can be derived. You don't need to memorize, but it's good to know the both relationships, as they will become handy for us to study or solve when we are solving the questions. Okay. So how is the power and energy related in an inductor? Now, I know the voltage and I know the current, and I know the definition of the power, right? Power equals the voltage times current. It's universal and it's always valid. So if we do the math, we can calculate the power relationship for an inductor. So power equals to V times I, and I substitute the V as L times di over dt, and I have another I here. So the power becomes L times I times di over dt. Now from here, I also know the current in terms of the voltage. I can substitute that here as V times 1 over L from T0 to tau plus I T0. If it's non-zero, we have to include this initial condition, constant if it exists. So the power relation can be obtained like this. For the energy, we know that the power is defined as the energy or the work done in unit time. So we can define the power as the work over dt. Okay, and if we substitute our power relationship that we have found here, we can simply get rid of the dt's, and we obtain a relationship like dw equals to li times di. Now, if I integrate both sides, I can get rid of the differential operator here and obtain the work function or the energy relationship for the inductor. So from 0 to W, the x is the dummy integration variable, equals to L times from 0 to I y dy. Again, here y is the dummy integration variable. Y dy, if you take the integral of it, it's going to be 1 over 2 times y to the square. And from 0 to I just put the boundary values, and I obtain it as 1 over 2 times I square. And I have to multiply it with this constant L. And on this side, I will obtain W minus 0, which makes W. So W equals to 1 over 2 times L times I squared. Now, this shows that the inductor stores energy when it has a non-zero current flowing. As you can see, this is interesting. So when we have some non-zero current flowing through an inductor, the energy is stored. And that energy is stored in the magnetic field surrounding the inductor. So let's solve another example to get more insight into the inductors. For the first example, given plot the current, voltage, power, and energy versus time, and align them in time so that we can have a better understanding of each variable's behavior. In what time the interval is the energy being stored in the inductor? In what time interval energy is being extracted from the inductor? What's the maximum energy stored in the inductor? And evaluate the integrals and comment on their significance. And we are given two integrals from 0 to 0.2 pdt and from 0.2 to infinity pdt. As you remember, 0.2 was the point at which we get this, maximum current value. So let us solve this. Now, if we draw the, waveforms, we have this, current relationship. We have found this, and we also calculated the voltage. The voltage change polarity, as you can see, at 0.2, which gives us an indication, because when we multiply voltage and the current, we are going to get the power waveform. As you can see, the power waveform has some portion positive and another portion negative. And the energy is typically defined as the area under the power curve, because we are taking the integral with respect to time, which is basically the computation of the area under the power curve. So at some point we have some positive power, and at some point we have some negative power. Now, from our previous classes, we know what does that mean actually. An increasing energy typically shows that energy is being stored. But if you look at the energy, waveform, which is basically the integral value of the power waveform, as the energy is increased, it means that we are storing energy, and it will reach to some maximum value. And after that maximum value, it will be dissipated. It will get smaller and smaller, which means that up to the 0.2 seconds, we will be storing energy, and after the 0.2 seconds, we will be dissipating energy. It's apparent because here the voltage polarity changes, so the power polarity changes. When we have positive power, we are basically storing the energy in the magnetic field, and when that energy becomes negative, then we will be returning the stored energy back to circuit that we are connected to. So this is how we can comment on the waveforms that we obtained by solving the example 1. And throughout example 2, we have discovered that when the polarity of voltage changes across the inductor, there is a change from energy storage to energy dissipation, or from energy delivery, let's say. Okay. Uh, so energy is at maximum when the current is at maximum, as you can also see. Like this is reasonable because we have just derived the relationship, energy and current relationship. It was 1/2 times L times I square. So when the I is maximum, I square will also get its maximum value proportional, and we will get the energy maximized. So as you can see from these curves, the we got the energy at a maximum when the current is at the maximum. So we can confirm this, and we can also compute this. If you just plug in the numerical values into the equations, the maximum current value is found out to be 0.736 amps, and because of this you can calculate the maximum energy, which is 27.07 millijoules. And for the part E, like from example 1, we have the IT is equaling to 10 times T times e to the minus 5t amps, and the inductance value is 0.1 Henry. If we do the math, the power between the 0 and 0.2 seconds can be computed. And if we take the integral, then we will be calculating the energy. So the energy difference at time equals to 0.2 and time equals to 0 can be computed as 1/2 times L times I square. Okay, the difference at different time points can be computed, and if we do the math, we have stored 27.07 millijoules when we are charging the inductor in this region, like between 0 and 0.2. We have simply stored 27 millijoules, and after 0.2, when the voltage polarity changes, we start to deliver that stored energy back to the external circuit. So if you do the math, like from 0.2 to infinity, our energy stored is basically, sorry, the energy returned or delivered is minus 27.07. Now, it's important to note that the total sum of power is zero, as expected. So the energy is conserved. We have just stored energy in the magnetic field for a short duration, and then we have returned that back to the external circuit. Uh, like as I mentioned before, based on the definition of power, the area under the plot of power versus T represents the energy expanded over the interval of integration. So the integration of the power between 0 and 0.2 represents the energy stored in the inductor during this interval. And the integral of P over the interval 0.2 to infinity is the energy extracted or energy returned to the external circuit. So in this time interval, all the energy that's originally stored is removed or taken back. So after the current peak has passed, no energy is stored in the inductor. So our energy storage is only between 0 and 0.2. When we reach our peak, after that peak, there is no storage, energy storage available. We will be, using the stored energy, basically. This is how inductors operate with respect to time. Uh, they they will need currents or that change with respect to time. So we introduce the alternating currents, and we will be working on the alternating current circuits mostly when we are dealing with inductors and capacitors, because under direct current conditions, the inductor is a short circuit and the capacitor will be an open circuit, as we will explore. Now let us take a closer look to the capacitor and its symbol and how it operates. Uh, Basically, a capacitor is just a two parallel plate of metals, conductors, insulated by some material, some dielectric material. And the displacement of charge creates an electrostatic field, and this field is used to store the energy. So when there is displacement in the charge, there will be some, energy stored in the electrostatic field. So you can think of it like a spring. When you compress a spring, you just store the energy, and when you release it, it will return you the energy that you have stored in the system. Like you can establish some mechanical analogies between these components and basic physics knowledge. The circuit parameter of capacitance is represented by the letter C, and it's measured in farads, and the symbol is basically a parallel, two short parallel conductive plates. Because of since the farad is a very huge, variable, basically a very large quantity in practical terms, the capacitors that we use in real world circuits are typically have values changing from picofarads to microfarads. So we have picofarads, we have microfarads, we have nanofarads. In microelectronics, when we are designing chips, we deal with very small capacitances in the range of femtofarads. So the graphic symbol is a reminder that the capacitance occurs when the electrical conductors are separated by some dielectric or insulating material. So there are situations that you obtain unintended capacitances out of your physical circuit design. These are called the parasitic capacitances. They are not physical components, but they exist as a result of your design, or as a result of the physics, basically. So this condition implies electric charge is not transported through the capacitor. Okay, it's displaced, but basically it's an open circuit. So the capacitor only conducts current when the voltage across it changes, and the direction of the current when this happens uh, follows the voltage polarity. So from a positive potential to a negative potential, and this potential difference is the voltage, as we know, the current follows the higher potential to lower potential direction. So the reference direction is chosen like this. Now, the terminal equation for a capacitor is given as the current I equals to C times dV over dt. As you can see, the current is proportional to the derivative of the voltage times some capacitance value. So if we pull the dt next to I can create an expression I dt equals C dV. And if I integrate both sides with respect to the voltage and the time variables, I can get this integration, like integral from Vt0 to Vt dx equals to 1 over C times integral of I dt from t0 to t. Now, if you take the integral, and if you put the boundaries for this integral, we observe that the Vt is equal to the 1 over C times integral of I d tau from t0 to t plus an initial voltage value V t0. So if the t0 is taken as 0, we obtain the voltage relationship that we derived from the current voltage relationship. So as usual, like you need to know this relationship because in order to be able to solve questions, you need to know the current to voltage relationship or voltage to current relationship, so that you can apply this to solve the questions. Again, we after finding the voltage and the current relationship, we can take a look at or compute the power and the energy. Uh, So if I multiply the voltage with the current, then I can compute the power. And if I take the integral of power between some time interval, I can compute the energy stored in a capacitor. Let us take a look at it. As I mentioned, the power is equals to V times I. And if we simply plug in the relationships that we have learned so far, the terminal equations, we will obtain C times V times dV over dt. C times dV over dt is the current, and the V is the voltage. So we have this. It's easy to understand. Then the power can be rewritten also as I times 1 over C integral of I dt from t0 to t plus v t0. If you know the voltage, you can write it this way. If you know the current, you can write it this way. Eventually, they are equivalent. They should give the same value. And since the energy can be defined as d work equals to c times v times dv, and the power is defined as the work done in unit time. There is the dt here, there is also a dt, and we just cancel them out. Then take the integral of both sides to get rid of the differential operator. So we will be able to obtain the energy relationship. If we do the math, we are going to get W minus 0 equals to 1 over 2 times C times V square. As you can see, the capacitor stores energy when there is a change in the voltage across its terminals. Now, this is interesting because in the inductor, we had the current here, current L times I square. So when there's a change in the current, the inductor will store the energy. And when there's a change in voltage, the capacitor will store this amount of energy. And we use this a lot in practical circuits to store and take back the energy to do certain work. Now we can simply solve an example to have a better understanding of the behavior of capacitance. In example 3, the voltage pulse described by the following equation is imposed across the terminals of a 0.5 microfarad capacitor, which makes it a 500 nanofarad capacitor. So Vt is defined as for the t smaller than equal to 0, the Vt is 0, and between 0 seconds and 1 seconds it's 40, so it's a linear function. And after the 1 seconds we have 4 times e to the minus t minus 1 volts. Now, according to this information, we are asked to derive the expressions for the capacitor current, voltage, and energy, power and energy. And we are asked to sketch the voltage, current, power, and energy as functions of time and inspect their relationship. And in part C, specify the interval of time when energy is being stored in the capacitor, and specify the interval of time when energy is being delivered by the capacitor. And in part E, evaluate the integrals and comment on their significance. And here these integrals are given as from 0 to 1 pdt and from 1 to infinity pdt. So these are actually the energy, this corresponds to, energies. So let us solve this question. Well, for the first part, we know that from the terminal equation of the capacitor, we know that the current is proportional to the derivative of the time derivative of the voltage times the capacitance. We know the capacitance is 0.5 micro. So I just need to take the derivative and multiply it with C. So 0.5 times 10 to the minus 6 represents the 0.5 microfarads, and dV over dt is 0 when the t is smaller than equal to 0. So I have 0 here. And for the interval between 0 and 1, if I take the derivative, it was a linear function, so the slope of that line is 4, and this will be a constant value that corresponds to 2 microamps. And for the for t larger than 1 seconds, if you take the derivative of this expression, you are going to get minus 2 times e to the minus t minus 1 microamp. So this is the current, the relationship for the voltage given. Now I know the voltage and I know the current. I can compute the power because power equals to V times I for always. I already calculated the I, and the V is given to me. So if we multiply each term within the intervals that corresponds each other, 0 times 0 will give 0 times 0 will give 0, and 2 microamps times the 4t would give me 8t microwatts for time interval between 0 and 1 seconds. And for the last part, for when t is greater than 1 seconds, I'm going to get minus 8 times e to the minus 2 times t minus 1 microwatts. Okay, so we have computed the power function for the capacitor. Since we know the power relationship in these three different intervals, we can also compute the energy for these intervals, because energy equals to the integral of power over an interval, and we have these intervals. Okay, so we can simply take the integral of these expressions that we have found, then put the boundaries and then compute the energy and obtain the energy expressions. An easier approach is simply use the formula 1 over 2 times C times V square. We are given the voltage at in the question. So I just need to compute the squares of each elements and multiply them with 1 over 2C. Okay. If we do the math, we are going to get 1 over 2 times. For the first interval, we have 0, okay, because power is 0. So if you take the interval, it's 0. Or if you do the math here, like voltage was 0, when the voltage is 0, the energy is also 0. For the interval between 0 and 1, we have 1 over 2 times 0.5 times 16 times t square, which would give us 40 square microjoules. And for t greater than equal to 1, we have 1 over 2 times 0.5 times 16 e to the minus 2 times t minus 1. That would yield 4 times e to the minus 2 times t minus 1 microjoules. Okay. Now, if we plot these four functions, the voltage, the current, the power, and the energy, we encounter, and if we align them with respect to time, we will get these waveforms, as you can see. So the energy is being stored in the capacitor whenever the power is positive. So if I take a look at the power waveform, as you can see, there is some positive portion and there is some negative portion. Now, when the energy is positive, I'm storing energy in the electric field basically. And when the energy is, the power is negative, I'm drawing current from it. So I'm taking the stored energy back from my capacitor. Okay. So during 0 and 1 seconds, I store the energy, and after 1 seconds, I draw the energy back. And the integral of the PDT is basically the area under this curve. So I have this curve, and I compute the area by taking the interval. And if I plot it, I will have the energy, equation, energy expression. As you can see, the energy increases between 0 and 1, and then after 1, it will be decreasing because I'm, taking back the energy that I have stored. Uh, so if we simply take a look at the first integral, it's the energy stored when the capacitor is, charging, and we have stored 4 microjoules. If you do the math, as you can see here, and after the 1 second period, we will have a negative value of energy, which means that we have drawn energy. So the capacitor is acting like a DC voltage source and providing voltage to the rest of the circuit, energy to the rest of the circuit, it means. So we have minus 4 microjoules. And if we sum or add them together, we obtain 0, which is expected because the total energy stored and restored must be 0 by the rule of conservation of energy. So the total energy is basically 0 according to this. And it makes sense, as you can figure out. So let us continue and learn about the series and parallel combinations of inductances and capacitances. Just like in the case of the resistors, we can combine inductors and capacitances, and we can obtain the equivalent formulation for this. Let us assume that we have 3 inductors, L1, L2, and L3, and let us assume that we have serially connected them. Now they share the same current, and they will have different voltages, obviously. So if you write down the equation for each voltage value, the V1 will be equal to L1 times di over dt. V2 will be L2 times di over dt, and V3 will be L3 times di over dt. All the voltage across these 3 components will be the sum of voltages. So I have, like, we can tell it by the KVL, the Kirchhoff's voltage law. The voltage across these will be added together, and since the reference directions are the same, they will be added together. So if we do the math, the L1 plus L2 plus L3 times di over dt is obtained. Now, assume that we have a one inductor that is equivalent to the behavior of these 3 inductors. Then that inductor will have some L equivalent times di over dt. So these di over dt's will be the same, and they can cancel out. Then the equivalent inductance is obtained as L1 plus L2 plus L3 plus, like how many inductors you have. Let's say you have n inductors connected in series, then you will need to add all the inductances together. Just like it's very similar to the case of the resistors. So inductors are summed when we have a series connection. So this is how we can compute an equivalent inductance out of series connected inductances. Another scenario is the situation where we have a parallel combination of the inductance. When we have parallel combination here, in our toy problem, we have 3 inductances, and they have some initial current T0, I1 T0, I2 T0, and I3 T0, and their currents I1, I2, and I3 when combined together will give us some current according to the KCL. And there is some voltage drop across the components, and they share the same voltage drop. Okay, so I can use the current relationship, and I can write down the currents with respect to the voltage because they all share the same voltage. So I can write I1 as I1 equals to 1 over L1 integral of V dt plus I1 T0. I2 equals to 1 over L2 times integral of V dt plus I2 T0. And I3 equals 1 over L3 times, V dt plus I3 0. From here, I can simply see that the current, the total current entering this circuit is the sum of three currents according to the Kirchhoff's current law for this circuit node. So I equals to I1 plus I2 plus I3 can be written. If I add these, I obtain 1 over L1 plus 1 over L2 plus 1 over L3 times the integral of VDT, because that voltage is same for all components, plus their initial value currents if they have. That is I1 T0, I2 T0, and I3 T0. Now, if we think that this is equivalent, if we think that there's an inductor which is equivalent to this combination of three inductors, then it should have something like this: 1 over L equivalent times integral from T0 to T V dt plus some I T0. And from here we can establish equivalence, and we can see that 1 over L equivalent would be equal to the 1 over L1 plus 1 over L2 plus 1 over L3. In addition, the initial condition for that equivalent inductance IT0 should be equal to the I1 times T0 plus I2 times T0 plus I3 times T0. So this is what we have obtained here, is that when we create a parallel connection of inductors, we add the reciprocals of inductors, and we obtain the reciprocal of the equivalent inductor. Just like in the case of the resistors, when we have a parallel combination of inductors, we compute it by summing 1 over L1 plus 1 over L2. If there are n inductors, then you have to add n of them, 1 over Ln, let's say. And there's some, when you obtain the result, you have to take the reciprocity of it to compute the equivalent inductance. So let us continue with the next slide to explore about the capacitance connections. So we can also have capacitances connected in series or parallel. Now let's take a look what we can do with the capacitors. If we have n capacitors connected in series like this, we can see that they will be sharing the same current. When something is connected in series, they will share the same current, okay? And the voltage across the components, all components, will be the sum of individual voltages, okay? If the capacitors have some initial voltage, V1 T0, V2 T0 to Vn T0, okay? We have to consider them as well. Now we know that the voltage across the capacitors can be computed as 1 over C times integral from 0 to T I d tau plus V0. If we establish an equivalence, if we think that these series connected n capacitors act like a big one big capacitance, how would it work? Well, just like we have done before, you will have to write the V1 and V2 and Vn, then you sum them, and at that point we are going to see that the equivalent capacitance will be the 1 over sum of reciprocals of the capacitances, okay? And the voltage across the overall components will be the sum of their initial conditions. So if we have some initial conditions assigned, then the initial condition of the equivalent capacitance is the sum of those initial voltages. In the capacitance, when we connect them in series, we obtain smaller capacitance, as you can see. this is interesting because it's the opposite when you compare it to the volt when you compare it to the relation of the resistors and inductors. So if you know the resistor, you already know how the combinations of the inductances, and if you take the opposite of it, then you will obtain the relationship of what you do to compute the equivalent capacitances. So you can memorize or remember it like this. For the capacitance, things are a bit of opposite and different. Now, if we take a closer look at the parallel combination of capacitance, when we combine n capacitances in parallel, they will be sharing the same voltage, as you can see. And there will be different currents from I1, I2 to In, and their sum will be equal to the equivalent current that is flowing into this circuit. So if we equate this into an equivalent capacitance circuit, we know that the I equals to C times dV over dt. So I1 will be C1 times dV over dt, and I2 will be C2 times dV over dt, and so forth. In will be equal to Cn times dV over dt. Since all the dV over dt's are the same because we have the same voltage across all the capacitors, we can simply add the currents according to the Kirchhoff's current law at this circuit node. So the total current will be I1 plus I2 plus until In, and it means that the C1 plus C2 plus C3 plus to the Cn times dV over dt. So if we simply establish an equivalence, then the dV over dt's will be reduced, and we end up with C equivalent equals to C1 plus C2 plus until the end of the Cn. So when we have parallel capacitances, we simply add the capacitance values to compute the equivalent capacitance. So in order to increase the capacitance, you need parallel combinations of capacitances. This is again opposite when you compare it to the case of the resistors or inductors. However, this is how the equivalent capacitances are found. You simply add them. If you have parallel connections, it's very easy to compute the equivalent capacitance. If you have a series connection, then you have to deal with the reciprocals, which might be a bit of cumbersome, but computable, given the fact that we have scientific calculators. So it can be done. After this, let us take a let us talk about the mutual inductance. This is something interesting. Now we can have different inductors, and we also know that the inductors store energy in the magnetic field. The magnetic fields can interact with each other if the components inductors are physically placed close together. So one magnetic field in an inductor can affect the magnetic field in another inductor. This is called the mutual inductance because we treat them as these two inductances coupled together as a single inductor kind of a thing. This has many uses in practice. For instance, transformers are the first example. We use transformers to isolate high voltage circuits from low voltage circuits. We use them to transform impedances and transform energy from high voltage to low voltage. For instance, in your wall adapters, like let's say you have some device operating at 9 volts. When you plug it into 220 volts, the voltage is reduced to 9 volts through this method of mutual inductance. So in practice, there are lots of different applications. So we need to learn and know about the concept. Normally, each inductance will have some self-inductance. That is what we have defined so far. And we can have some coupling between these inductors. Uh, it's defined by K, typically a number between 0 and 1. And the mutual inductance is defined as K times square root of L1 times L2. Okay. So if the inductances are very closely, coupled, you will have large K values. If they are far away, they will have, smaller K values. They will affect each other loosely. And sometimes if you want to transfer this the magnetic field, we use magnetic cores. These cores are built based on ferromagnetic materials that capture the magnetic flux and transfer it. Toroids and the iron cores that are used in transformers are such materials, so that we can control the coupling and the mutual inductance precisely. And we have a dot convention, as you can see here in this circuit. Uh, it's essential to explain what that means. Basically, when the reference direction for a current that enters the dotted terminal of a coil, the reference polarity of the voltage that it induces in the other coil is positive at the dotted terminal. So, for instance, in this particular example, I have a voltage source, VG, I have a resistor, R1, and I have an L1 here. So since the dot is here, I am assuming that the positive polarity is here. So this is higher potential, and I will have a negative sign here. And this inductor is coupled to L2. Somehow they are coupled, and there is some mutual inductance in between. And in the second part of the circuit, which is galvanically isolated, there is no current flow from here to here, but magnetic field allows us to couple the circuit and control the current on the other side. We have a polarity of dot here, as you can see. So it's opposing. So I will have a negative and a positive one here. So what does that mean? If the voltage is increasing on this side, on the side of the L1, then the voltage will be in opposite direction on the side of L2. Just inverting, okay? It's just inverting. If it's increasing, this is decreasing, plus there is some uh, coefficient that is multiplied with the magnitude, uh, is also applied. And I have a second resistor which dissipates the energy transferred to the secondary side. So this is the story about the dot convention. When you see the dot, you can easily apply the polarity of the voltage, and then establish your Kirchhoff's voltage and current laws accordingly. Now, if we just write down these equations and take a closer look, I can simply write down a KVL on the primary side, and I'm taking the clockwise direction. So VG will be minus because of that, and I1 times R1 is positive, so I have positive here and a negative here, and I have a positive here and a negative here because my dot is here. I know it by heart. And the voltage defined as L1 times D1 over dt. And because of the mutual inductance, the L2 also affects this side, okay, by amount of M, because its magnetic field will somehow affect and adversely affect, because they are opposing each other, as you can see. So it will try to reduce the voltage at this point, okay? So it will create some, reverse polarity. And as a result, I'm just, computing it as a negative, because with negative sign, because it's opposing the direction of current flow. So it will have a negative sign, as you can see here. So their sum should be 0 on the primary side. I can also write down a similar equation of KVL on the secondary side. And since I'm taking the direction of you know, uh, clockwise as my reference, I'm rotating in the same direction as L2, so L2 times di over dt will have positive value. However, because of this coupling and mutual inductance, I will have some effect coming from the primary side, which is proportional to the di1 over dt. So m times di1 over dt will be opposing the direction that I'm rotating. So it will have a negative sign. It will be reducing my voltage. And there is also the R2, which I take as positive to negative. So like the R2, I2 times R2 plus L2 times di2 over dt minus m times di1 over dt equals to 0. So this is how we use when there is some mutual inductance, this is how we construct our equations. We have to think about the effect of the other side on our side. As you can see, both sides affect each other. The secondary side affects the primary side, and also the primary side affects the secondary side because of this coupling effect. Because these inductors are located closely, so they affect each other. I hope this makes sense. It might sound a bit of confusing at the beginning, but it's actually reasonable as long as the inductors are coupled together. So how do we define these dot markings in practice? Let's say we have some inductors, some toroid or some iron core. How do we define by inspecting the physical structure of an inductor? Typically, uh, like these mutual inductance requires two inductors coupled somehow. And as I mentioned before, these ferromagnetic materials are used to confine the magnetic field lines inside their physical bodies. And once the electromagnetic field generated on one side is transferred to the other side, and that magnetic energy induces a current on the other side, and vice versa. This is bidirectional. So this is how they work. As you can see, the physically currents are isolated. Like one side current doesn't mix up with the other side current, so this provides an isolation. However, they can interact with each other. So we arbitrarily select one terminal. Let's say we select the D and mark it with a dot. Okay. Arbitrarily, we have to start at some point. We just put a dot on some uh, side of the inductor coil. Then we assign a current into the dotted terminal and we label it as ID. Then we can use the right-hand rule that we have learned in physics to determine the direction of the magnetic field established by ID inside these coupled coils and label this field as phi d. Okay. Arbitrarily, then we pick one terminal of the second coil. Let's say we just obtain, like we choose the terminal A, and we assign a current into this terminal, showing it as IA. Now again, we use the right-hand rule because this magnetic core is continuous. So the phi d will be transferred to here as phi a, okay? And that phi a will induce some current, so that direction can be found with again applying the right-hand rule. And when we apply it, the direction of the flux established by IA inside the coupled coils, which is denoted by phi a. Now we compare the directions of the two fluxes, phi d and phi a. If the fluxes have the same reference direction, we place the dot on the terminal of the second coil where the test current IA enters. Like in the figure here, like we have the fluxes of phi d and phi a have the same reference direction, as you can see. As a result, the dot goes onto terminal A. If the fluxes have different reference directions, then we have to change the dot on the terminal of the second coil where the test current leaves. Okay, this is how we identify the reference directions on a physical, mutually coupled inductor. If we have some measurement capability, things are much easier. If you have some voltage source and if you have some multimeter that can measure the volts, then we can simply build a circuit like this. We just need to, close the switch, and at the instance of closing the switch, some voltage will be induced on the other side, because uh, although this is a DC voltage, there will be some transient current flow until the short circuit current is established, which will be VBB over R, because since this is a DC voltage, the inductor eventually become a short circuit, so the maximum current is VBB over R. If there is no R, then infinite current will flow, which means that your circuit will explode or get damaged. So there's always need some there's always need for some resistance to limit the current through the circuit, and this maximum current is VBB over R. Now, when I close this switch, because of the rise of the voltage, because of the rise of the current, there will be some voltage induced, and it will induce some magnetic field, which is coupled to the other side, and then that coupled magnetic field will induce another current, and that current can be, measured if it's connected to a load, or if there is no load here, we can directly measure the induced voltage. Now, the key point is I arbitrarily choose that this is the positive side, and I just put a dot there. And when I close the switch, if the voltage spike that I observe on the other side is positive, then it means that the polarity is positive. So I put my dot on this upper side. If the voltage spike that I observed through the multimeter shows some negative value, then it means the other side should have the dot, because it's opposing me. When I'm increasing the voltage here, it is showing me negative voltage, which means that it's going down. So it should have the dot located here. So this is how you can identify or model the real world, mutual inductors using some measurement approach. Okay. So, like when the switch is closed, the voltmeter deflection is observed, and the momentary deflection is, if it's upscale, I mean, if you measure some positive voltage increasing, then it means the coil terminal connected to the positive terminal of the voltmeter, so it will receive the polarity mark, the dot. Otherwise, if the deflection is downscale, that is, if you measure some negative voltage on the other side, here the coil terminal is connected to the negative terminal of the voltmeter, and it will receive a negative, polarity mark accordingly. This is how you can use the experimental method to identify the dot points and their relationships by measurement. So let us also think about a circuit. How do we handle circuits that contain, inductors? In example 4, we are given a circuit which has some, constant current source and some resistors and some inductors. We are asked to write a set of mesh current equations that describe the circuit. We have the IG and I1 and I2 as our mesh currents, and all the component currents can be written in terms of the combinations of these, mesh currents, as you remember from chapter 4. So we need to verify that also if there is no energy stored in the circuit at t equals to 0, and if the Ig equals to 16 minus 16 times e to the minus 5 t amps, the solutions for I1 and I2 are I1 equals to 4 plus 64 times e to the minus 5t minus 68 times e to the minus 4t amps, and I2 is equals to 1 minus 52 times e to the minus 5t plus 51 times e to the minus 4t a. Basically, when we have the inductors or capacitors in a circuit, because of their terminal equations, we are going to get linear differential equations instead of only linear equations, as in the case of basic resistive circuits. So we have to solve differential equations to obtain the voltage and current values. Okay. Let us proceed with the solution and take a closer look of how we can establish our equations. Once you have your equations established, as usual, we can use the mathematical tools that we have in our hands to solve the problem. So for the first example, like for the first part, uh, we simply need to choose the polarities for the components, and since we have some mutual inductance here, somehow they are coupled, okay? And that coupling causes an 8 henries of mutual inductance between the 4 henry and the 16 henry inductor. We just keep it as a note. And since we know the dots, we know the polarities basically, plus and minus signs. And then I can write down KVL in 3 loops, uh, keeping in mind that I will choose any reference direction for the resistors. I'm free to choose any reference direction as long as I'm consistent throughout the whole solution. I will obtain some polarity out of it, some positive or negative value. If it's positive, then the current is flowing in the original direction that I have determined. If it's negative, then it means that it's flowing in the opposite direction. If I write down my equations, then I will obtain 4 times di1 over dt plus 8 times d over dt ig minus I2, because here in the because of the mutual inductance between them, there will be some opposing voltage drop across the 16 Henry inductance. So I have to account for it, and the current of the 16 Henry inductor can be written as Ig minus I2. This is why that current times the mutual inductance has to be accounted here. This looks weird, but because of this coupling effect, we have to consider that. Then 20 times I1 minus I2 and plus 5 times I1 minus Ig is used to compute uh, the circuit basically equals to 0. This is the KVL equation. And second one can also be written as 20 times I2 minus I1. I have I2 here and I1 here. And plus 6 times I2. So we have 60 ohm here and plus 60 ohm I2. And plus 16 times d over dt I2 minus Ig. For the 16 Henry, now we have the I2 minus Ig current that we need to consider, and minus 8 times di1 over dt. Now here, because of the mutual coupling, there will also be some negative opposing voltage induced because of this coupling. I have to write it down as well to counterbalance the expressions. Now we have established our equations and we can basically try to solve them. Typically Ig is known because it's a given value, so I have 2 equations and 2 unknowns, I1 and I2, and this can be solved uniquely. Solution was given to us and the question asks for verification. So I just need to substitute the value of I1 and I2 into this equation and then do the math and see if it's consistent as a solution. Okay. So this is how we handle circuits that contain inductors. So if we substitute, then we will see that it simply works. Now, if we go back to our original discussion at the beginning of the this course, we talked about the proximity switches. Typically, they use capacitive approach and charge sharing between the two capacitors, because our body is also a capacitor and keeps some, can have some charge on it. So we are when we touch a proximity switch, there will be some charge exchange between us and the switch. So this can be detected uh, as a touch and can be registered as a button pressed. Uh, so if you look at the circuit, equivalent circuit, we basically have uh, some C1 and we also have a capacitive voltage divider. And when we touch the button, we just get connected in parallel with the circuit. Some of the charge will flow into our body or from our body to the circuit, and this is harmless because the current is very limited, and we are talking about electrostatic charge displacement, which will induce a change in capacitance. And a circuit that measures the capacitance continuously can identify uh, or register a button touch. Okay. Now, typically, the actual values of capacitors are in the range of 10 to 50 picofarads, depending on the geometry of the switch and how the finger is inserted, and like whether the person has some gloves or so on and so forth. Like there are different conditions, but more or less it's in the range of 10 to 50 picofarads. Now, when we touch it, like we can simply explore it through an example. Assume that all the capacitors have the same value of 25 picofarads. Okay. Also assume that the elevator call button is placed in the capacitive equivalent of a voltage divider circuit as shown in this figure. We have some variable voltage, some AC voltage applied. We have the button, which is some sort of capacitor, and we have also a fixed capacitor. So the voltage will be shared between two capacitors. When nobody touches, and if the all capacitances are 25 puffs, then like some half of the voltage will be on this capacitor. Then this can be measured by a microcontroller or some other means to identify if there has been any touch to the button. So as the first step, we need to calculate the output voltage when there is no finger present, and we also do it when there's some finger present. And the difference will tell us to detect how to detect the existence of someone touching the button. Okay, so let's do it. Now we have basically, like, if you think of it like a voltage divider, and if you do the math, the dV over dt will be C1 over C1 plus C2 times dVs over dt. So uh, there will be some, voltage division between these C1 and C2. And from here, C1 times dV minus Vs over dt plus C2 times dV over dt equals to 0. Now we know that the Vs equals to 0.5 times VST originally, okay, because it was they both have 25 picofarads, okay. So from here, when nobody touches, our voltage at across the C2 can be written as C1 over C1 plus C2 times VST plus V0, the initial voltage value. Typically it's 0, but we need to write it so that we are mathematically, correct. So if we do the math, again, C1 times dV minus Vs over dt plus C2 times dV over dt plus C3 times dV over dt should be equal to 0. And from here, I can pull dV over dt as C1 over C1 plus C2 plus C3 times dVs over dt. And from here, Vt equals to C1 bolup divided by C1 plus C2 plus C3 times Vst plus V0. Now, since all the capacitances are equivalent 25 picofarads, then we can reach a conclusion that the Vt will be 0.33 Vst. Okay. Now, when we don't press the button, we had 0.5 as our solution, as you can see here. This can be measured. Okay. When we touched, we are going to get 0.3 times of Vst. So the difference is we can identify a button pressed or a button unpressed condition. Okay. Using some, of course, extra analog circuits required to, condition the circuit. So in the new circuit, when we combine them, we are going to get this, including the, all the capacitive effects. This becomes our, circuit that's required to solve. And we can use the parallel series combination rules to, calculate the total capacitance accordingly to make life easy for everyone. So in summary, today we have learned about the inductance, its terminal equation definitions, its characteristics, and its voltage, current, power, and energy equations. And the same applies for capacitance. We learned about the terminal equations of capacitance and the voltage and the current and the power and the energy characteristics and equations. Then we continued with the series and parallel combinations of capacitances and inductors. We also learned about the mutual inductance and the importance of coupling in a circuit. When the circuits are coupled, it's not that easy. You have to do some, extra math to, solve the circuit, because each coupling creates some opposing extra voltages. When you are writing down the KVL equations, you have to include that effect. And depending on the direction of the coils on the transformer core, we have to take these directions into account when we are writing down equations. If the dots are the same in parallel on both sides, then the voltage polarities will be the same. If they are opposing each other, the voltage polarities also will follow, and they will be opposing each other. We have learned those things. So that will be all for this week, and thank you for your participation. See you next time.